I hand over to you last week. Everything okay? So, everyone already contacted the student assistant for the lab course? Yeah? Okay. Someone started already? Oh. That's nice. So, let me go over then to the plan of this lecture. What I would like to show you today is first of all a discussion of the exercises, and there are two exercises. One with respect to a proof of correctness for the cumulative frequency. And there was already a question, do we have to expect more of these proofs? Well, sometimes there is a proof of correctness, but always it's meant to give you additional insight in a program. And I think that especially for this cumulative frequency program that we discussed last week, if you present a proof of correctness, then it becomes clear what the structure of the program is. And moreover, you are certain that there are no mistakes, no things left to bring clarity in the construction of the program. So we will do that after discussing the rest of the program. As you might know, during the lab course, we have to do some matrix manipulations. And to start with these matrix manipulations, we need to discuss some of the matrix operations by parallel computing. And today I would like to discuss the inner product operation, the matrix vector product operation, and the matrix multiplication operation. And we will see that, well, in this case, for the simplest case already, the prefix computations take a very important role. Then we will discuss the next basic technique, and that's pointer jumping. And pointer jumping is a technique that you can use to identify nodes in a tree or in a graph. And so as soon as you use some kind of pointer structure, graph structure in your data structure, then you can imagine that some nodes play a different role and act as a kind of identifier for a cluster of nodes. Well, if you would like to know for each node in such a cluster to what, well, special node it belongs to, then you use this technique of pointer jumping. Then finally, we will discuss our third technique, and that's divide and conquer. And we will mainly illustrate this technique that should be familiar when you did your algorithms course in the bachelor. We will discuss this technique using a particular example, that is a quite difficult example, finding the minimum one index in an array. Well, with respect to the examples, I should warn you that during the lecture, the most difficult examples will be discussed. And why are we doing that? Well, I think that, well, once you know how a difficult example is solved, then, well, it should be an easy case. If the same example or a variant of this example shows up during the exam. Yeah? So discussing the most difficult examples here during class gives you an advantage when you're doing the examination. And I promise that they will not be that difficult anymore if you know what's going on when we discuss this in class. So this is the program, and I would like to start now with discussing this proof of correctness of the cumulative frequency program. And this program was discussed last time in class, and here is the structure of this program. So, in order to compute, given an array A, an array of cumulative frequencies, we execute this program, If there is only one element, then of course we are immediately ready. Else, what we do is we halve the size of the array by taking sums here of adjacent elements in the array A and storing them in the first half of a new array B. Yeah? So B has the size 1 to n divided by 2. Then we take the same program, cumulative frequency now, but we apply it to B, so to half of the array, to the sums here that we collected. We compute the final result, and then we analyze case by case what should be done to compute the cumulative frequencies for the original array A. If I is even, then we are ready. Ci equals to zi divided by 2. Then I equals 1, C1 equals A1, and LCI equals zi divided by minus 1 divided by 2 plus AI. Yeah? So this seems to be a strange program, and now the idea is if we provide a proof of correctness, then maybe the structure of the program becomes clear. So I already indicated, together we indicated that a proof by mathematical induction would be most appropriate, and that we will do. So the proof is, and I hope it's visible from this room for the people in the backside too. So proof is by mathematical induction, and now we have, of course, to come up with the object of induction, and that's over K in n is to the power K. No? And that's, of course, a decision you have to make quite intelligently. And the idea is, well, if you would like to apply induction here, you see that, well, once we call cumulative frequency with n elements, then it is reduced in the first recursive call to an array of n divided by 2. Yeah? So if we have once an array of n is 2 to the power k, then the call of the inductive step is on n prime is 2 to the power k minus 1. So the induction should follow the structure of the program too. So we apply it to k is 1 to, and in n is 2 to the power k. Okay, then you know that a proof by mathematical induction starts with the base case. K equals 0. Well, this implies n is 2 to the power 0 is 1. Well, in that case, what the program will do is if n equals 1, then C1 equals A1. Yeah? Okay, sorry. Here of course, I forgot here to mention what exactly we have to prove here, and that's of course that's the elements of the array C correspond to what's mentioned there. Yeah? Okay. Well, in that case, line 1 is executed. And we have 1 equals sigma A j. J less than or equal to 1 is A. Yeah? And that's a correct statement, of course. Yeah? So for n is 1, it holds. Then the induction. Assumption. Suppose Ci is sigma A j holds for all arrays A. With k less than or equal to n, yeah, or some n, and then the inductive step. Let k equals to n plus 1, and now we should be able to prove that the proposition, namely Ci equals the sum of the first I elements, holds also for arrays of size n plus 1. Yeah? Okay, so assume k is equal to n plus 1. Let A 1, 2, 2 to the power n plus 1 be given. Yeah. Well, since m is equal to, obviously, is at least as large as 0, k is at least as large as 1, so that means that now statement 2 is executed. Yeah? Since n is 2 to the power m plus 1 is larger than 1, statement 2 is executed. And that implies that for all I between 1 and n divided by 2, and well, now n divided by 2 is now 2 to the power n, bi equals a, and then 2I minus 1 plus a 2I. Yeah? Okay. Now, after that, we execute line number 3. But now, an important property can be established with respect to the outcome here of Z. Note that here we have an array of n divided by 2. So that means an array of 2 to the power m. And that means that k is less than or equal to m. And that means that for those arrays, the induction hypothesis holds. Yeah? So we are sure that for after execution of step 3, there is a relationship between Z and B. Z is the cumulative frequency array with respect to B. By induction hypothesis, now it holds that for every I between 1 and n divided by 2, and that's 2 to the power n, we have Zi equals Bj for j equals, so for j between 1 and I. Yeah? That's my induction hypothesis. Okay. Now call this line 1, call this 2, and now you can combine 1 and 2, and you get we obtain Zi equals the sum of, and now 2j minus 1 plus a 2j, and that's for j. Can you give me the outcome of this expression? So can you simplify this expression? So starting with j equal to 1, you obtain here a1 and a2. Then j becomes 2, and it becomes a3 and a4. Then a5 and a6, a7, a8, etc. So the result is that in Zi, I obtain the cumulative frequency of the first 2 I elements. Yeah? So, here, believe it or not, but this is equal to A, and then J for j between 1 and 2. Yeah? And, well, that's very easy to see. We just saw that no element of A is skipped. Yeah? So it ranges from 1 to, and then the last element, well, fill in here j equals to I, and you obtain 2I. Yeah? So it is the cumulative frequency of the first 2I elements. Yeah? So this is really equal to what I would like to obtain, Ci, isn't it? Okay. Okay. Now, so this is a very important result we now obtain. And now we have to perform the rest of the program in order to derive our expression for Ci. But what you see now is that, in fact, for all the even positions in the array, we already computed the cumulative frequencies. Yeah? And now we have to obtain the cumulative frequencies for all the elements. Well, and that's quite easy to do because, well, if I equals 1, that's a special even odd position, then you just have to copy A1. And if you have other odd positions, then what you do is you obtain the nearest even position that precedes that off position. Yeah. So for example, C5, you compute C4, 4 is even, you can obtain that directly from the array Z, and then you add just one element, additional element to it to obtain the final result. So the idea now is hereafter we execute line 4. Then we obtain for I equals 1, C1 equals A1, and that is sigma A J less than or equal to 1. For I is even, we have Ci can be directly obtained from, well, what should be the result? Here we have the correspondence between Zi equals the sum of Aj for j between 1 and 2I. So if we take for I is even Zi divided by 2, then the correspondence here tells us that we will have all elements up to I. Yeah. And for I larger than 1 and I is odd, we have Ci is equal to Zi minus 1 divided by 2 plus Ai, and that again is equal to Aj for j less than equal to I, because Zi minus 1 divided by 2 I minus 1 is even. Yeah? So I minus 1 divided by 2 gives you the cumulative sum of the first I minus 1 elements. That's the result we obtained there. So this is the cumulative result of all the first I minus 1 elements. If you add to that Ai, then you obtain the sum of the first I elements. Yeah. So, well, now take this qualitatively, and now the outcome is Ci equals the sum for all I is 1 up to 2 to the power n plus 1. Yeah? Well, now the result of mathematical induction tells you that if you can prove that the theorem holds, or the property holds, for k equals 0, and you can show that the property holds for all, if the property holds for a fixed k, then it holds for k plus 1, 2, then the property should hold for all k. Yeah? So in this case, the property should indeed hold for all k is 1 to an arbitrary value. Yeah? Okay, well, the basic idea here is that, well, by following this proof very closely, you should discover that indeed here the key fact is this relationship. And this relationship, by mathematical induction, tells you that you can find, by repeated calls of cumulative frequency, the cumulative frequencies of the even positions in the original array very easily. That's purely done by repeated application of this recursive step. And then, by realizing that given that fact, you can obtain the cumulative frequencies for all the positions quite easily, and by reducing it to finding a position, an even position, like here, the rest is done. Okay, so please keep that in mind if you have to find, if you find it very difficult to get the idea of a program, apply a correctness proof and it will turn out to be much easier than you thought. Okay. A second exercise that we discussed last week was an application of this technique, balanced tree technique, to a particular problem, and that was finding patterns in a sequence. In this case, it was finding weakly increasing runs in a sequence of numbers. And the problem here is a little bit easier. It asks you to find weekly, whether or not there exists a weekly increasing run of a given size. Okay. And you say that such a run exists, weekly increasing run exists, if the property AI less than or equal to AI plus 1 holds for at least k of those elements. Now you have to decide in log n parallel time whether A contains a weekly increasing run of at least size k. We know that there exist sequential algorithms that can do it in a time of O(n), but we have to do it significantly faster. And the purpose of this exercise is to give you an idea how you can handle these kinds of exercises, because often it will appear that the real difficulty in such an exercise is not in finding which technique you have to apply. Here even it was prescribed what kind of technique you have to apply, but in finding the right definition of the operator you have to use in order to combine elements. So for example, in finding the maximum, you had to combine two elements and find a partial sum. Yeah? Sometimes you have to multiply, like for example in finding the inner product. But here we have a special operator and you need to define it yourself. And I must warn you, the resulting operator that we have to define here, if we follow this approach for this exercise, is quite complicated. But again, don't be afraid, I will never ask you to do so during an examination, but once you have seen how it can be done, it becomes much and much easier to do it for a new exercise. So let's go through this idea. What we will do is the following, and that's almost always the initial step that you have to perform. You have to copy the results of comparing two adjacent elements in the array into a new array. Sometimes you have to copy the literal results, and sometimes you have to abstract and just indicate whether or not a relationship holds. Well, if you want to detect runs, it's quite natural to make pairwise comparisons and assign it a 1 if indeed the comparison corresponds to a part of a run, and a 0 if not. Yeah? So if AI is less than or equal to AI plus 1, you assign it a 1, and else you assign it a 0. And then we have two special cases, and that we call sentinels. And you know from algorithms and data structures and for algorithms that sentinels play a very important role. You can use them to detect the end of your operations. So here B0 and Bn acts as ends of the array. So you know when to stop and when to start. Then you use a balanced tree of computation to determine the length of the runs and whether there is a run of at least length k. And that's the easy part. Once you have found you have found the initial data structure on which you can apply this prefix computation scheme, then you are ready. But we have to find a new binary operator that can be used to determine the length of the runs. And well, I will use an exercise to make you aware of the difficulties. And that's a general recipe. And so once you have an exercise at your exam, please always use an example to detect what the difficulties are that you have to deal with. So suppose here we have an array A, and it consists of these numbers. And we need to decide whether or not A contains a run of at least k equals to 5. What we do is the following. We copy the results of comparing AI with AI plus 1 in an array B. And we use these sentinels, B0, so this is B0, and then we compare A1 with A2, ends up in the success, A2 with A3, success, success, then not a success because 4 is larger than 1, and until then we continue. And here, well, this is a simple trick. If, for example, you know in a prefix scheme you have to use elements whose number equals a power of 2. If there are too few, then you simply add here neutral elements 0. Because if 0 is a sentinel here at the end, then well, you will never go beyond that 0. Okay. So you fill here until n is a power of 2. Okay, so now we have to be aware of this array P. And of course, with your eyes, now it's very easy to detect here a success. Here we have a series of 5 ones. But how to let your program detect that there is a series of 5 consecutive ones? So please be aware that now I can apply this, the rest of the program also to the problem of detecting consecutive series in a sequence of numbers. Okay. Well, I will apply the length by a balanced tree method. And well, the easiest way is first to analyze it and then refine your method. Because when you start, you will try to find the most easiest method, and then by finding more complicated cases, you will detect some errors in your approach. Let's just start here, and very naively. So here we see that we have to combine a 0 with a 1. What does that mean? That means that we start with an initial segment of a possible run, isn't it? So we have to remember that in a certain sense. So it does not suffice to translate this result just in a 1, because then you would forget that you are starting an initial segment. Okay. So what I do here, I just take the 0 and the 1 just to remember me that I'm starting a sequence. If I have to compare 2 ones, there is no problem, because that means, well, either I'm in the beginning, I'm in the middle, or I'm at the end of some initial segment. I don't know, but the only thing I know is that there are 2 adjacent numbers. Yeah? So that means that possibly I can extend my run. And I remember that 1 combined with 1 gives 2. Then here, I'm again starting a possibly new segment, yeah, or ending a segment. So I remember the 0 and the 1. Here also the 0 and the 1. Then 2, 2, and here I've only zeros. So I've reduced now my sequence to this sequence. And now I have to come up, well, also with a definition of this operator that is able to deal with these pairs of numbers, yeah, instead of ordinary numbers. So, well, let's now extend my definition. What would be the outcome, you think, what the best outcome of combining 0, 1 with 2? If I have only to use local information, eh? Yes?
Move the boundary.
Yeah, so what?
That would be 0, 3.
Okay. Quite okay. Yes, because here you have a 1, so you know that there is at least 1, 1. Then it's followed by 2 elements, so the result should be an initial possible run of at least 3 elements. Yeah? Here, well, what should be the outcome? I have a start of a possible run that's ended here. Okay, so what I do have to remember here is only the start of a possible run. Yeah? Because this run, I can simply forget. It can't be extended anymore. Yeah? Do you see here? 0, 1, 0, 1. The only way to extend it is to use this right half. Yeah? Okay, then here I have 2 and 2 gives 4, 0 and 0 gives 0. And now I'm almost there. I have to combine this element with that element. So 2 pairs. What will be the outcome? Yeah?
0, 1.
Yeah. Why? Well, this is not a success because k should be equal to 5. Yeah? It ends here because I can't extend this possible initial segment of a run because here it ends. Yeah? And there is a new run starting. So the only possible combination here gives, the only possible result here is 0, 1. Then here I have 4 and I combine it with 0. That means I have a run of at least 4 elements and it ends here. Yeah? And now combining it, it gives me true. Yeah? Why? Well, here I have to combine a possible run starting with one successful element, and I combine it here with 4, and it's actually 2. Yeah? Yes?
If you put in a swapping condition that looks at whether or not you reach the right length already, then it should be complexity of k, right? Instead of log n.
No. Why would it be k?
Because
you have to, in fact, you have to compare all the pairs. In principle, in the worst case.
don't you, if there is a sequence of 5, so
Yeah.
a length of 5,
Yeah.
don't you see that within 5 rounds?
No. Well, of course, you can detect it, but then, so your question is, should I detect some true?
Yes.
Yeah, of course, you can detect a true in, well, let's say k steps. But then, then your problem is not solved because the final result should be true. Yeah. So you have to continue in order to come up with the true. This true should be, so you have some, let's say, in parallel processing, you have assigned to some processor the task of extracting the final result. And the final result should come to it. Right. It's the same problem as detecting, for example, whether or not there, what the first position is of a 1, for example, in an array. You have to find out. There exists such a 1, but to detect its position, it requires additional processing. Okay, so what is the problem now here? Well, we have to come up with the definition of this operator. And this operator, well, it sounds amazingly simple, but its definition is quite complex. So here you have two base cases. 0 combined with 0 will give you a 0. 0 combined with an x, if x is larger than 0, well, this means you start with an initial segment and you have to remember what x is. Yeah? Here you have 0 and you start a new segment. Well, you have to remember just the start of the new segment. Here you have 0 and you have an x 0, well, then the outcome will be true if x is larger, of at least as large as k minus 1. If you make k minus 1 comparisons, you have k elements. A run of k elements needs k minus 1 comparisons of adjacent elements. And 0 else, and then you might have here even a triple. X, 0, y, and combined with 0 gives true if x is at least as large as k minus 1 and is 0, y else. And so you continue. And this is not the last. Here we have to find. Yeah? So, it's only, well, of course I can't give such an exercise at the examination, don't be afraid. But, well, what is important is that you get the idea of the necessity of defining sometimes a rather complex operation in order to use it in prefix computations. And once this definition is given, then the prefix computation is very simple. You just run the program here, and here it is. Use the following balanced tree scheme. Here we have the definition of the b's, b0, bn, and I just assume that n is sufficient here, and otherwise you add the zeros. And then you follow the prefix scheme. So for h is 1 to log n plus 1, for j between 1 plus n to the power h minus 1, etc. Combine here the elements, so bj equals b2j combined with bj plus 1, and return b0. What will be the result? Well, if b0 contains true, then you know that there is such a sequence. If b0, oh, sorry, I have to add here. No, sorry. I should, of course, give here the final result. So if it contains true, then you know that such a run has been found, and else, well, there is a triple, there is a number or whatsoever that's unequal to true. You know that it is false. Yeah? Is that clear? So the difficult step here was to come up with this definition of the binary operator, but, well, of course there are more simple cases that you now can do quite easily. And the general recipe is, once you have to come up with such a scheme, please remember this case and try to find a definition of a binary operator that makes it easy for you to use this balanced tree scheme. Well, after the break, we will continue with the prefix computation, the pointer jumping.